So far we've looked at several problems where mechanical energy was conserved. So if you take the potential energy from all of your conservative forces, such as gravitational potential energy and spring potential energy, and you add to that the kinetic energy, that will give you the total mechanical energy. And we saw that this total mechanical energy was conserved. And if there are no conservative forces present, this will generally be true. Total mechanical energy is conserved. So if you have a problem that doesn't have friction or some other non-conservative force, you can write down that the sum of all of the different types of mechanical energy initially is equal to that same sum finally, and then solve for any of the unknowns that you have in your problem. If, on the other hand, there are non-conservative forces, such as friction present, then you will have to take that into account. The change in the energy of the system will be equal to the work done by any of these non-conservative forces. So we can write that as that work done by non-conservative forces is equal to the change in mechanical energy. Or, putting that out in more terms, the change in mechanical energy of the system, which is equal to the work done by the non-conservative force, is equal to the change in the kinetic energy, or the final minus initial kinetic energy, plus the change in the potential energy, or the final minus initial potential energy. And keep in mind, you're going to need one final minus initial potential energy term for each kind of potential energy that's present in your problem, be it gravitational potential energy or spring potential energy. So let's take a look at an example where we use this concept of the change in the energy being equal to the work done by a non-conservative force. So in this example, we have a 70-kilogram diver stepping off a 10-meter tower, dropping straight down into the water. So as he's dropping from the tower to the water, we're going to assume air resistance is very, very small, and so that part of the motion, there is no non-conservative force. Once the diver enters the water, however, they're going to come to rest 5 meters beneath the surface, and we need to find the average resistance force exerted on him by the water. So once the diver is in the water, there is a resistance force, a non-conservative force acting, and we need to figure out what the amount of that resistance force is if the diver is brought to rest 5 meters beneath the surface of the water. So we really have two parts to this problem. A part where there are no non-conservative forces, and then a second part in the water where there are non-conservative forces. So let's draw a picture showing the different parts of the motion. So first off, the diver starts on a diving board, and the diving board is above the surface of the water. So here's the diving board, and then here is the surface of the water. And the diver is diving from the board into the water. So after the diver enters the water, then the diver is going to go through the water until they come to rest at some point beneath the surface of the water. So the next thing we need to do is figure out where is y equals 0? Where are we going to set our y equals 0 level? We need to do that so we can be consistent throughout the problem. And I'm going to set y equals 0 equal to the water level. So I'll say that the surface of the water is where y equals 0 is. I could put the y equals 0 down here, I could put it up here, and then all the other y's would be negative. It really doesn't matter. So I'll choose the surface of the water as being my y equals 0 point. Then when the diver's on the diving board, that is at 10 meters. So the diving board is at y equals 10 meters. And when the diver comes to rest beneath the surface of the water, that occurs at y is equal to minus 5 meters, or 5 meters below my y equals 0 point. Now, as I mentioned before, there are two different parts to the motion. there's the part that's in air. And here, the work done by non-conservative forces is 0. Here we can conserve mechanical energy. Here, the work being done by non-conservative forces in the water is not equal to 0. Here there is a resistance force. That resistance force is doing work, taking energy, taking mechanical energy away from the diver. So first, let's look at the air part of this problem. So we'll look at the part where the diver is flying through the air. Here, the work done by non-conservative forces is 0. We can conserve total mechanical energy. So we can write down all the different types of mechanical energy. We have mgy initial, the initial gravitational potential energy. There aren't any springs here, so I don't have to worry about spring potential energy. Plus the kinetic energy, 1/2 mv initial squared. And those are all the kinds of energy that are involved initially, and that's going to be equal to mgy final plus 1/2 mv final squared. So the thing that I'd really like to know, I know the height initially, and I know that when the person steps off the diving board initially they're not moving, so initially the velocity is 0. And I know the final, so I really want to know what is the final speed of the diver right when they reach the surface of the water. So as we mentioned before, we can make this simpler by setting some of these quantities equal to 0. Initially, the moment the diver steps off the diving board, they have not started falling yet, they do not have any speed, so their initial kinetic energy is 0. And when the diver reaches the surface of the water, I've defined that as my y equals 0 point. So the potential energy, gravitational potential energy, is 0 at the water level. So then I can set the two remaining terms equal to each other. So basically what I have is some initial gravitational potential energy turns into kinetic energy. Okay, so then to solve for V final, let's see, I can divide both terms by m, so the mass of the diver cancels. I can also multiply both sides of the equation by 2, which cancels with the 1/2. So V final squared is equal to 2 times g. And then I can take the square root of both sides. And so my V final is going to be equal to the, and to 2g times y initial. Shouldn't forget the y initial there. And so the V final is going to be equal to the square root of 2 times 9.8 meters per second squared times the initial height, which was 10 meters. So that's going to give me a final velocity of about 14 meters per second. All right, so that is the final velocity. That's the velocity when the diver reaches the surface of the water. So this is at the water surface. Okay, so next let's look at the water part of the motion once the diver enters the water. When the diver's entering the water, we know that there is a non-conservative force. There's this water resistance force at play. And so the work done by this resistance force, this non-conservative resistance force, is going to be equal to the change in the energy. So it's going to be equal to the change in the kinetic energy plus the change in the potential energy. So the change in the kinetic energy would be 1/2 mv final squared minus 1/2 mv initial squared. That's the change in the kinetic energy. And the change in the potential energy is going to be equal to mg y final minus mg y initial. So those would be the changes in the different kinds of energy. I can also write down what the work done by this non-conservative force is in terms of the definition of work. I know that work is always equal to the amount of force times the amount of displacement times the cosine of the angle between the force and the displacement vectors. Okay, so in this case, if I think about the diver when he's in the water, the resistance force pushing on the diver is slowing him down. So that must mean that this resistance force is in the upward direction, because the resistance force is taking away from his downward velocity, and it's causing him to slow and eventually come to rest. The displacement of the diver, on the other hand, is in the downward direction. So the diver's displacement, they're moving in the downward direction as they're slowing and coming to rest. So the angle between these two vectors is going to be equal to 180 degrees. So this would be the cosine of 180, and the cosine of 180 degrees is equal to -1. So the work being done by this non-conservative force is going to be equal to negative the amount of the force times the amount of the displacement. And the displacement when the diver is in the water, they're going from y equals 0 to y equals -5 meters. So the amount of displacement would be equal to 5 meters. So then I can set this equal to the work done by non-conservative forces equal to this term, or this expression. But before I do that, I should see if I can simplify things by setting any of these, or seeing if any of these are equal to 0. So let's see, the final kinetic energy. Well, we're talking about the diver's passage through the water, and when the diver gets to this final point, this final depth, this is when the diver comes to rest. So the final velocity of the diver would be 0, the final kinetic energy would be 0. Initially, as the diver is entering the water, we know that the diver is going 14 meters per second. So this term is not 0. The final potential energy, well, finally, the diver is going to be 5 meters below the surface of the water. And what about initially? So initially, the diver is at the surface of the water, and so y initial would be equal to 0. So this term also is going to be equal to 0. Okay, so then I can set these two expressions for the work being done by a non-conservative force equal to each other. So I have minus the amount of resistance force times 5 meters is going to be equal to 1/2 mv initial squared plus mgy final. And the thing that I want to find is I want to find the amount of force. So let's see, the amount of force is going to be equal to 1/2 mv initial. Oh, there should be a minus sign here. Yes, I should carry this minus sign down. So this is a minus, so this is minus here, and so this is minus, and this is minus, plus mgy final, and then all of this gets divided by minus 5 meters. Okay, so then I just need to plug in values. I have a negative 1/2. The mass of the diver is 70 kilograms, and this is squared. The initial velocity as the diver enters the water is 14 meters per second, so that's 14 meters per second squared plus 70 kilograms times 9.8 meters per second squared, and then that's also times the y final, which is negative 5 meters, and then all of that gets divided by negative 5 meters. So if I put that into my calculator, I'm going to get an amount of force equal to 2,058 newtons. And so that is the average resistance force that is acting on the diver. So next, let's consider this question. Can the potential energy of a system be negative?